Hey guys! Hope everyone has had a really good weekend so far. I just wanted to share with y'all a little video on balancing redox reactions. This is something that we covered pretty briefly in class, but after talking with Dr. Zahn on Friday, it is going to be something that's going to be quite important for your test and also the rest of your chemistry career. So I thought I'd just post a little video that gives you a couple of different options for how to work these problems, and these ways make more sense to me, and for the guys who came to SI, I prefer this way over the answer keys way. So anyways, here it goes. And if you want to kind of follow along, this is covered in chapter 4, section 11 of your book, and that begins around page 128. Okay, so basically when it comes down to balancing redox reactions, and that's our reduction, oxidation, there are two main methods that you can use. There's the oxidation states method, and then there's also the half reaction method, where you take the whole big equation and then break it into two tinier half reactions, one for oxidation and one for reduction. But what has to be taken into consideration there is whether or not you're in acidic or basic conditions, because the rules change slightly depending on the whatever type of solution you're balancing in. But the first way to work these I want to go over is the oxidation states method. We're just going to go over a couple of steps and then work a problem together. So in the oxidation states method, these are the steps you want to follow. So first, just as we've been practicing, you want to assign oxidation states to all atoms. Then, once we assign the oxidation states, we want to determine how they've changed. We want to see which species have been reduced and which have been oxidized. And then based on those changes, we're going to choose coefficients for our reactants based on however much our oxidation state changes. And step 3 will make more sense here in a minute. And then once we complete step 3, the rest of the equation we can balance just purely by inspection. And that's just kind of the way we're used to, looking at the species and say, oh, okay, 1 carbon here and 2 carbons here. I need to write a 2 in front of this carbon. But anyways, let's just start by doing an example. So we're going to follow our first step, which says assign oxidation states to all atoms. And in assigning oxidation states, you typically want to start by assigning oxygens and then hydrogens first. But since we don't have any hydrogens here, we'll just start with oxygen. So oxygen almost always has an oxidation state of -2. Let me write that in a different color. It may be easier for y'all to see. Okay, of -2. Alright, also going to be -2 over here. Okay. And then we know that any element that's just in its pure form has an oxidation state of 0. So that accounts for aluminum and then manganese. Alright, but over here we have a manganese paired with 2 oxygens. So if each oxygen is -2, that means that this whole thing is -4. And so since this entire compound is neutral, then we know that we need a +4 to cancel out our -4. Okay, now let's move over here and do the same thing. This time we have 3 oxygens who each have the charge of -2, so that brings us to a total charge of -6. So in order for the aluminums to cancel that out, we need a total charge of +6. But that's going to be divided between 2 of them, so the oxidation state of each aluminum is +3. And this is an important point because when you're writing the oxidation states, you want it to be per element. So the little numbers on top are for each aluminum, not both of them. Okay, so check, we've done step 1. So now we need to see if any oxidation states have changed. So let's take a look. Let's just start from left to right. So manganese over here, it starts as a +4, and then it goes to a 0. Okay, so this oxidation state has decreased. it's becoming less positive. We started at a positive 4, and then it's worked its way back down to 0. So in order to do that, we know that we were adding electrons. So in this case, if we were doing the half reaction method, electrons would go on this side because they're being added in. Okay, so if we're adding electrons, this manganese is going to be oxidized. And oxidized is when you gain electrons. Okay, so let's keep checking. So we know our oxygen doesn't change, -2 there and -2 here. But let's check out aluminum. So now when we see aluminum, it starts as 0, and then it changes to +3. So its oxidation state is becoming more positive. That means it's losing electrons. So that means it's been reduced. Loses electrons. And the way I remember this is kind of a handy phrase that's oil rig, or some of you all may have learned Leo the lion says grr. But what this stands for is it says oxidation is loss of electrons and reduction is gain of electrons. So that can kind of help you keep those things straight in your mind. And so while the aluminum is being reduced, its name is going to be the oxidant. So whatever, or you may see it also called the oxidizing agent. So whatever is being reduced is itself the oxidant, and whatever is being oxidized is itself the reductant or the reducing agent. And this will be really key for you all to kind of get a good grasp on how to use these terms, because it can get a little confusing. Alright, so we've done step 2. Yay for us, halfway there. Okay, so now to step 3, choosing our coefficients. So basically, we've seen that manganese, right here, has decreased by 4, while aluminum has increased by 3. So now what we're after is to find the least common multiple of 4 and 3. And so in this case, that would be 12, because 3 and 4 are both factors of 12. Now we ask ourselves, okay, what do we have to multiply 4 by to get us to 12? And the answer to that would be 3. And now we ask, well, what do we have to multiply 3 by to get us to 12? And that answer would be 4. Okay, guys, so the numbers that I've just written in blue, which is what we have to multiply by to get to that least common multiple, these numbers become the new coefficients of the reactants, key word, this is important, in our equation. So where we see manganese as a reactant, over here, we're going to multiply that by 3. Okay, now where we see aluminum as a reactant, we're going to multiply that by 4. Let's squeeze that in there. Okay, so now that we've done that, step 3, now we can balance the rest of the equation by inspection. Okay, so now let's just look at it just like we would any other equation. So we have 3 manganese over here. We need 3 over here, so let's multiply this by 3. Okay, so that seems good. Now let's take our aluminum. So we typically kind of want to save the oxygens for last. So our aluminum here we have 4, and here we have 2. So we can multiply this aluminum by 2 to get 4. Okay, so that's good. So now let's check out our oxygens. So here we have 3 times 2, which is 6. Ah, nice. Here we have 2 times 3, which is also 6. So all of our atoms have balanced. as well as the total charge. This side is neutral. When we speak of total charge, we're not talking about oxidation states. We're just talking about the literal charge of the molecule, like MnO2 is neutral. And so it's a neutral charge on both sides. And so that checks as well. All right, so that's how to use the oxidation states method to balance a redox reaction. Okay, so now let's move on to talk about how to balance using the half reaction method in acidic conditions.